Welcome to Information Service Engineering. This is lecture number 5, Basic Machine Learning. In this part of the lecture, I will give you a short introduction to machine learning in general. Okay, let's start. Let's start with the question, how do we learn? First, we have to understand how learning really works before we are transferring these kind of technology to machines like a computer. Okay, let's have a look at the general learning process. How does this work usually for you? How do you learn something? So what you do is you recognize that last time you were in a specific situation, you tried out a particular action, which means you saw some data and for that data you gave a specific output. Now you have two possibilities. If this output was correct, so if you found out that this was the correct solution, you will try it again in the same way. If it wasn't correct, so then you will have to come up with something different. So this is the basic principle how you learn. You try out something, if it works, it's well. If it doesn't work, make something different. So we make an observation, we remember, we adapt, and this is the most interesting goal of learning, we generalize. So we try to adapt similar solutions to similar problems. And we try to categorize these problems according to our solution strategies. So this is the basic principle of learning. And the basic learning process is rather similar, regardless whether the learner now is a human or a machine. So it starts all with data storage, which means it utilizes observation, memory, and recall to provide a factual basis for further reasoning. Then, of course, all what you see have to be abstracted, so you have to do abstraction, and this involves the translation of your stored data into a broader representation and broader concepts. Based on that abstraction, you try to do a generalization, which means this uses the abstracted data to create knowledge and inferences that drive action in new contexts. And then, of course, you have to evaluate it, find out whether it was correct or not, and this provides feedback. A feedback mechanism to measure the utility of learned knowledge and inform potential improvements. So that's the basic learning process, no matter whether it's human or machine. So you start with the data storage, then you go further with abstraction, try based on that to achieve generalization, you apply your knowledge, and then you have to do an evaluation and probably recalculate and retry. So this is the basic process that we continuously go through also in machine learning. Okay, now we are prepared to come up with the first definition of what is machine learning. So this is a formal definition. So a computer program is said to learn from experience E with respect to some class of tasks, T, so it learns something specific, and performance measure P, so we have to evaluate it according to a specific performance measure, if its performance at task in T, as measured by P, improves with experience E. So this is machine learning. The program is said that it learns from experience regarding some tasks, regarding some performance measure, if this performance measure for a task improves with its experience. Okay, based on that, let's have a look at some machine learning applications. One rather popular machine learning application is so-called collaborative filtering. This is a basic statistical technique that is, for example, applied in many e-commerce portals. So people who have bought that would also buy this one. So you get a suggestion, and this is based on so-called collaborative filtering. You could implement this in different ways. A non-machine learning approach would go the following way. So always recommend the most popular items. So this strategy works for a significant number of cases. It's like the top 10 effect. What sells best? Recommend it to somebody. The likelihood is rather high that this guy will also buy the same. On the other hand, you could also implement a prediction mechanism and to try to predict interesting items based on previous actions and decisions of similar users. And this is really the basis of statistical machine learning and statistical collaborative filtering. So this is an interesting first approach for machine learning. Another task in machine learning would be automated translation, which means translation of a text from a source language into a target language, while of course preserving its meaning, its semantics. You could also implement this again in two different ways. First, you could fully understand a text before translating it, using a curated set of rules which are crafted by computational linguists who are well versed in the two languages you want to translate. So you would have to fix rules. But on the other hand, you could also learn them. And we could learn this by example. So use examples of translated text in the two languages we would like to translate and to learn how to translate simply from these examples. This would be the learning-based approach to automated translation, which is also used with rather high success today. Another thing that we already know from our natural language processing lecture is named entity recognition. There you have to identify entity types in natural language text, such as, for example, persons, places, organization, time, etc., etc. Again, you could implement that by using handcrafted rules and filter out entity types, but of course, you don't have to. You could also, again, use examples of marked up documents to learn dependencies automatically. So, learning involves also generalization. It could really learn what does it mean, what is a person, for example, and what are the interesting features that are required to learn what is a person. And then you could identify identity types with it. Another rather popular task is visual concept detection. For sure you have seen this probably in an app with your smartphone. And this means there are descriptive categories assigned to images based on their visual content. Again, this could be implemented by using handcrafted rules that are applied on features extracted from the images to classify the image. But on the other hand, using the machine learning approach, what you would do is you learn to classify the images from examples of marked up images. And you even learn what are the best suited features to be extracted from these image examples to achieve the best classification results. Visual concept detection already works near human level. This is a rather specific example, which dates back to the early 1950s. You might remember from the last part of the lecture when I showed you the Mark I perceptron from 1957. So here it's handwritten digit recognition. This was also the task of the very first neural network. And if you want to formalize that, it's quite simple. You have here these 10 different digits. They are represented in a 28 by 28 pixel matrix. And usually what you do is this input is encoded in form of a vector, which means if it's white, then for example, this position is 0. If it's black or blue, this position then is 1. And then you have a vector. And this vector comes from a vector space which has 784 dimensions if you have 28 by 28 pixels. And then you learn a classifier that you here refer to as a function f of x, such that f assigns with the input x a specific output class, which is between 0 and 9. So this would be handwritten digit recognition. Okay, these were several famous popular applications where machine learning can be used. Let's now have a look on different categories of machine learning algorithms before we go into details. Okay, again, what is machine learning? In general, you could say these are algorithms that can improve their performance by using training data. Typically, here the algorithm has a large number of parameters and it's really difficult to learn, since the values are learned from the data, and there are situations where it's really challenging to define handcrafted rules somehow how these parameters should be interpreted. And exactly in this case is where it's difficult to see as a human the necessary generalization or the necessary rule, or whether there are too many rules or too difficult rules. There machine learning comes into place and can achieve sometimes even better results than a human can. Okay, but let's get back to the typical machine learning problems. One rather typical and rather simple task is the so-called binary classification tasks. There, given a pattern x drawn from some domain capital X, what you do is you estimate which value an associated binary random variable y, either +1 or 0 or +1 or -1, will assume. So you try to split a given set of items into two different classes. This is binary classification. If there is binary classification, then of course there should be also multi-label classification. You remember the handwriting example task. If you want to decipher, if you want to categorize handwriting, if you want to recognize handwriting, you do multi-label classification, since you get a pattern and then you assign to the pattern either 0, 1, 2, 3, 4, 5, up to 9. This is multi-label classification. So there, given a pattern X drawn from a domain capital X, you estimate which value an associated binary random variable Y, which can be of the value 1 to n, will assume in the end. So we distinguish between binary and multi-label classification. And then there is a specific problem which is called regression, or a specific class of problems, regression problems. There, this variable is a real value variable. So the goal of regression usually is to estimate a real valued variable Y from R given a specific pattern X. And this is a rather prominent example which can be used, for example, for the prediction of stock prices for a future date. So there you use usually something like linear regression. To distinguish what is used, if it's classification or regression, simply for regression usually you are dealing with so-called quantitative responses. So if your problem considers quantitative responses, then it's a regression problem. If your problem involves qualitative responses, so if you have to assign your patterns or specific patterns in simple drawers, then it's a classification problem. So this is the basic difference or the basic distinction between classification and regression problems. And then you have two major classes that have to be distinguished. One is so-called supervised learning and the unsupervised learning. Let's first start with supervised learning. In supervised learning, usually what you have a training set of examples with according correct responses. This is provided as your training set. And then what your algorithm does, it generalizes to respond correctly for all these possible outputs. And typically, each example is a pair consisting of some input object, which is usually a vector, and a desired output value. This is the so-called supervisory signal. You see here, what we have written here in natural language can also be expressed in a more formal mathematical way. What you have here, you have, some functions f, and you have your training data consisting of pairs x sub I and y sub I. And what you do is you try to find a specific function f prime that more or less assimilates the relation that y is f prime applied to xi. So if you learn that, if you approximate that via the learning step, then in a future prediction task, you might be presented new data, that is x here, and then you achieve a result by applying this function f prime, that was the target of your learning process, to exactly this previously unknown data, and you result in a prediction y that might be then the correct solution. So this is the basics of supervised learning. Overall, of course, the process of supervised learning is much more complex. It starts with some data collection, pre-processing, sampling, and so on. And then you have the important learning process. So supervised learning always involves a so-called training or optimization phase, when exactly this function f prime has to be computed. And then, if you apply it, it's the so-called prediction phase. There you do a final classification, and of course you do also an evaluation to find out how well your learning has performed. So this is supervised learning. On the other hand, you also have unsupervised learning. There usually you don't have the results. What is not provided here are the answers, are the correct responses. What you try to do, you try to infer patterns. You try to infer a function to describe hidden structure from unlabeled data. There, again, the correct responses are not provided, but instead the algorithm tries to identify similarities between the inputs, to find patterns between the inputs, so that the inputs have something in common and are categorized together. So this is a purely statistical approach, and usually there you call this also density estimation. We will see examples for both for supervised learning and for unsupervised learning. Before then, we really go into the details of machine learning algorithms. So, this was a first tour around machine learning technologies. What we have to learn next is we will have a deeper look on evaluation and generalization, and we will see what kind of problems we are dealing with there.